Welcome back. In this section, we're going to revisit the problem from back in chapter 1.1, the area problem, where I have some sort of a curve and I'm looking to find the area underneath it. Before we get there, though, we need to have a little review of sigma notation from pre-calculus. When we have a summation like this, a1 added up to an, we could write it using this notation, our Greek letter sigma, meaning that we're going to sum things up. I is going from 1 to n, and we're adding up the AIs. So we'll add up A1, A2, A3, all the way up to AN. We call I the index of our summation, and 1 is our lower bound, and n is our upper bound for our summation. And AI, that's term number I of our sequence. Now, you'll remember summation, just like limits did, just like differentiation did. Limits and differentiation had a sum and constant multiple and difference property, and we've got the same thing going on here for our summations. If you have a summation of something where there's a constant multiple, you can take that constant multiple outside and just sum what's not a constant. And we had the same sort of thing going on with limits and differentiation. We would just sort of leave constant multiples alone. Or we could go term by term, doing limits term by term, differentiating term by term, or summing term by term, whether we're adding or whether we're subtracting. In addition to these summation properties, we also have the following summation formulas for adding up constants, adding up i's and I squareds and I cubes. So putting this together, because we can go term by term, because we have formulas for I square, I cubed, and we can do any constant multiple of them, then basically any polynomial that's in terms of i's we'll be able to sum as long as it's a polynomial of degree 3 or less. So that means that we could tackle problems like the following. If you're looking at this, we've got this function 3x squared minus 2x plus 1, and we want to find our summation f of I. So f of I, that'll be the value that we get when we put I in for x, and I is going to take on the values from 1 all the way up to n. So basically we're looking at f of 1 plus f of 2 plus f of 3 and so on all the way up to f of n. So let's get ourselves started. If we're looking at the summation of I equals 1 to n of f of n, of f of I rather, then that would be the summation of putting in I for all of my x's, the summation of 3i squared minus 2i plus 1. And I know number one that my summations will allow me to split things up term by term. So that's the sum from 1 to n of 3i squared minus the sum from 1 to n of 2i, and then plus the sum from 1 to n of I. Of 1 rather. And the other thing that I had was that constant multiples could be taken out front. So for the 3i squared, I could say really it's just 3 times the sum of the I squareds. And same thing with the second summation. I could take the 2 outside, and it's the sum of the i's from 1 to n. And the last one is just a constant. There's no need to take anything out, so it's just the sum of 1 from 1 to n. And now I'm just going to use the formulas from the previous page. The summation of the I squareds when we go from 1 to n is n times n plus 1 times 2n plus 1 all over 6. And the summation of I from 1 to n, the formula for that was n times n plus 1 over 2. And a summation of a constant from 1 to n is just n times that constant. So the only thing really left for me to do is just to do a little bit of cleaning things up. So firstly, I can say that for the first part, the 3 and the 6 I'll cancel, leaving just 2 in the denominator. For the second fraction, the 2 and the 2 will cancel, which means I won't have a fraction anymore. And then the last term, that's just going to be a single n. So what I'm going to have would be n times n plus 1 times 2n plus 1 all over 2, and then minus n times n plus 1, and then plus n. And if I wanted to go one step further, and why not, I could expand and simplify a little bit here. The expanding isn't too hard to do on the left-hand side. So if I were to multiply the numerator out for my first fraction, I would have 2n cubed 3n squared plus n all over 2. If I were to expand the next two terms, I'd have a minus n times n and a minus n times 1. And then that's kind of nice because now the minus n and the plus n will cancel each other out. And the last thing that I could do, I could just sort of combine these two together, and I suppose I could do that by making a common denominator. So I have minus n squared, but I'll sort of rephrase that as minus 2n squared over 2, so that I can say, well, I had 3n squared minus 2n squared, which is 1n squared. So 2n cubed plus 1 single n squared plus n all over 2. And there we go. So now we've got a formula that will give me the sum of f of 1, f of 2, f of 3, all the way up to f of n. And it's just in terms of n. So if I now wanted to find the sum from I equals 1 to 100, I could just put in 100 for n, and there I go. I would have all of my values for f of x all added together. Now, the reason why we're going to be talking about these summations is because we're going to use them in the service of finding the area under a curve. So for our problem, we've got a continuous curve. It's above the x-axis, and we want to find the area under the curve. And so if you'll remember back to 1.1, the idea was that we were going to split things up into rectangles. So basically the idea first starts off with us taking our interval that we're interested in and slicing it into subintervals, however many we'd like to have. So in the little pictures that I've got below, I've taken the interval from 1 to 3 and I've sliced it into 2 subintervals. I've got it from going from 1 to 2 and going from 2 to 3. And for each of those, delta x is the width of my subinterval. It's just the total distance from the two endpoints divided by however many subintervals you're looking for. The total distance between my two endpoints is 2 units, and I'm slicing it into 2 subintervals, so delta x is 2 divided by 2, or 1 unit. So each rectangle has a width of 1. So the next thing is my height. What is the height choice for my rectangles? And for this, there's lots of choices that you could pick. So in my first little subinterval from 1 to 2, I could pick the left endpoint and use the y value there as the height of my rectangle, or I could use the right endpoint and use the y value there as the height of my rectangle. And you can see that the choice of your endpoint does make an impact on whether the rectangle overestimates or underestimates. So when we're looking at this function 1 over x, if I'm looking at using my left endpoints, it looks like all of my rectangles are a little bit bigger. We wind up with an overestimate. And if I choose my little endpoints to be the right ones, then my rectangles are a little smaller than the curve. In other words, I get an underestimate. And there's lots of other options you could choose as well. You could choose the midpoint of the interval or any other place. For this course, though, for Math 100, we're always either going to ask you just to use left endpoints or right endpoints. So that's our idea. We've taken our interval from wherever to wherever, and we've sliced it into a bunch of subintervals. And CI, that's going to be whatever the point that we're choosing to take as the place where we find our y value. So whether CI is the left endpoint or the right endpoint or a mid endpoint, whatever it is, f of ci, that's the y value at that place. So in other words, we're going to take that to be the height of our rectangle. So then if you wanted the area of all of your rectangles, well, it's just your first interval, the y value there times the width, and the width is delta x. And then for the second interval, the y value there plus times the width, which is also delta x. In other words, we're going to have a bunch of things that are lengths times widths. All the widths involve delta x. So we could say that we have now a summation of just f of ci times delta x. And for this, the delta x will be a nice little constant for us. So if we wanted to, we could even think about taking that delta x out of the summation. So now coming back to where we were in chapter 1 when I introduced the problem, we also noticed that if we increase the number of rectangles that we work with, in other words, if we increase how many subintervals we have, we get less and less of a discrepancy between the area of the rectangles and the area under the curves. So when there's only 2 rectangles, there's quite a bit of a discrepancy, but if we increase it to 6 rectangles, even less discrepancy. We go even wilder, 10 subintervals, and even less of a discrepancy. We're closer and closer to the true value. And actually, the fun part is it's getting closer and closer to the true value, whether I started off taking left endpoints all along, or whether I started taking right endpoints all along, or any other point in the in-between. It really actually doesn't matter. That's why when I said back in the previous slide, CI is a point, and I didn't specify which kind of point it was, whether it was a left end point or a right end point, and that's because, in a sense, it doesn't really matter. Because we have the big idea here that if we're working with our hypothesis of we've got a nice continuous function, it's not below the x-axis, we've sliced it into a bunch of subintervals, they all have the same width of delta x, and take whatever ci you'd like in each subinterval, and if we look at the limit of the number of subintervals going to infinity. So if we increase it to as many rectangles as possible, the area of all of those rectangles will be the area under our curve.